What if I told you that one of the most dominant drag racing engines of all time was originally designed to haul city buses? Not race cars, not muscle cars, but buses. The kind that picked up your grandmother for her morning grocery run. This is the story of how General Motors accidentally created a drag racing monster while trying to solve a completely different problem, and how a bunch of hot rodders discovered that sometimes the secret to going fast isn't spinning an engine to the moon. It's about making power where nobody else was looking. Picture this. It's 1961, and you're standing in a GM engineering facility in Detroit. The room smells like machine oil and cigarette smoke. Engineers in white shirts and skinny ties are hunched over drafting tables, not designing the next Corvette engine, but working on something far more mundane, a power plant for commercial vehicles. Their mission? Create an engine that could move 40,000-pound buses through stop-and-go city traffic all day long without breaking a sweat. What they didn't know was that they were about to hand drag racers the most unlikely weapon in the history of the sport. Untold. The engine they were developing would become known as the GMC Twin 6, though most people called it the 702. And before you think this is just another story about some V8 that made good, let me stop you right there. This wasn't a V8. It wasn't a straight 6 either. It was a V12. Yes, General Motors built a gasoline V12 for trucks and buses, and it would go on to humiliate purpose-built race engines in ways that still make engineers scratch their heads today. To understand why this matters, we need to travel back to the late 1950s. The trucking industry had a problem. Diesel engines were expensive, complicated, and many fleet operators didn't have mechanics trained to work on them. But gasoline engines of the era couldn't deliver the low-end grunt needed to get heavy vehicles moving from a dead stop over and over again. City buses in particular were murder on engines. Every stoplight, every bus stop, every intersection meant hauling 20,000 pounds or more from 0 to 30 miles per hour. Do that a few hundred times a day, and most gasoline engines would either overheat or shake themselves apart. Enoch and GM's truck and coach division had been using their 401 cubic inch V6 in buses since 1957. It was a good engine, making around 190 horsepower and 355 pound-feet of torque. But fleet operators wanted more, not more speed. Buses didn't need to go fast. They needed more torque down low, where it mattered. They needed an engine that could accelerate a loaded bus away from a stop without the driver having to wind it out to 4,000 RPM and wake up the entire neighborhood. So what was GM's solution? Take two of their 351 cubic inch V6 engines and basically glue them together. I'm oversimplifying, but that's essentially what they did. They took the architecture of their existing V6, which itself was derived from their small block V8 with two cylinders lopped off, and created a 60-degree V12. The result was 702 cubic inches of displacement. That's 11.5 liters for those keeping track. Bigger than a Viper V10, bigger than a 7.0-liter Corvette LS7, bigger than basically anything you could get in a passenger car then or now. But here's where it gets interesting. GM didn't design this engine to rev. The red line was just 2,400 RPM. Let that sink in for a moment. Most performance engines of the era were considered lazy if they couldn't spin to at least 5,500 RPM. Small block Chevys were regularly twisted to 7,000 RPM or more in competition. But the 702, its peak power came at just 2,100 RPM. The specifications were bizarre by performance standards, but perfect for commercial use. The engine featured a 4.56-inch bore and 3.58-inch stroke. That's what engineers call or-over-squarer. The bore is bigger than the stroke. Usually, that's a recipe for high RPM operation, but GM used other tricks to optimize for low-speed torque. The compression ratio was a modest 7.51, designed to run on regular gasoline. The camshaft was basically agricultural in its specifications, with tons of duration and minimal overlap. The intake manifold was designed for velocity at low RPM, not high RPM flow. The carburation was handled by a single 4-barrel Rochester, jetted rich for pulling power. Result? In stock trim, the 702 made 250 horsepower at 2,100 RPM. That might not sound impressive until you hear the torque figure, 585 pound-feet at just 1,200 RPM. By 1,200 RPM, this engine was already making more torque than most big blocks made at their peak. It was exactly what bus operators wanted, an engine that could move heavy loads without drama, without stress, and without having to rev the nuts off it. Honor and GM built these engines from 1960 to 1965, installing them in buses, heavy trucks, and even some fire trucks. They were expensive to produce. That V12 configuration meant lots of parts, lots of machining, and a massive block that weighed over 1,000 pounds. But for commercial operators who needed maximum durability and low-end power, they were worth it. The 702 had a reputation for being basically indestructible in commercial service. Some logged over 500,000 miles hauling buses around cities without a rebuild. Now, here's where our story takes a turn. It's 1962, and drag racing is exploding across America. Every weekend, thousands of hot rodders are showing up at drag strips trying to go faster than the other guy. The formula was pretty well established. Take a lightweight car, stuff in the biggest engine you could find, spin it as high as you dared, and hope it held together for the quarter mile. Everybody knew that horsepower was just torque times RPM divided by 5,152. So if you wanted more horsepower, you needed to spin the engine faster. That's why guys were putting solid lifters, radical cams, and high compression pistons in their engines. RPM was king, netter, Tom Hoover. Not the Tom Hoover who designed the Chrysler Hemi, different guy. This Tom Hoover was a drag racer from Michigan who had a different theory. He figured that if you could make massive torque down low, you could get the car moving faster off the line. And in drag racing, the first 60 feet often determines who wins. While everyone else was chasing RPM, Hoover was chasing torque. 110 Hoover had heard about these GM bus engines through the grapevine. A buddy who worked at a Detroit Transit Authority mentioned that they were surplusing some old buses, and these things had V12s in them. V12s. Hoover bought a complete 702 engine for $200. That's about $2,000 in today's money. For reference, a new 409 Chevy big block cost about $500 at the time. The first thing Hoover noticed when he got the engine home was the sheer size of it. The 702 was 36 inches long, not counting the transmission. It was wider than a big block Chevy, and it was heavy. Even with aluminum intake manifold and without accessories, it still weighed nearly 800 pounds. Stuffing this thing into a drag car was going to be a challenge. But Hoover was committed to his theory. He shoehorned the 702 into a 1940 Willys coupe. If you know anything about Willys coupes, you know they were already popular in drag racing because they were light and had a good weight distribution for the strip. But nobody had ever tried to put a V12 in one before. Hoover had to modify the firewall, build custom motor mounts, and fabricate a header system from scratch. There were no aftermarket parts for the 702, no performance cams, no high-flow intakes, no racing pistons. Everything had to be custom or adapted from other engines. The first time Hoover fired up the 702-powered Willys at the local drag strip, people laughed. The engine had a distinctive sound, not the lumpy idle of a radical cam, but a smooth, almost turbine-like whir. It didn't rap and crack like the other cars, it just hummed. When Hoover staged at the starting line, his competitors were probably feeling pretty confident. After all, how fast could a bus engine be? The answer came at the first green light. The Willys didn't spin its tires like the other cars, it just hooked and moved. The massive torque of the 702, combined with the relatively light weight of the Willys, created a combination that nobody expected. While other cars were busy spinning their engines to 3,000 RPM trying to get the clutch out, the 702 was already making 585 pound-feet. The Willys would leap off the line like it was shot from a cannon. But here's the real kicker. Because the 702 made its power so low in the RPM range, Hoover could run a really tall gear ratio. While other racers were running 4.88 or 5.13 gears and shifting 3 times, Hoover could run a 3.73 gear and shift just twice. Less shifting meant less time lost. And because the engine was never stressed, remember, it was designed to run all day in a bus, it was incredibly consistent. Run after run, the 702 would deliver identical times. Ensign Hoover's first published time slips showed the Willys running 12.8 seconds at 108 miles per hour. In 1962, that was seriously quick for a gasoline-powered car. Many big block cars with twice the RPM capability couldn't match it. Word started to spread through the drag racing community. That guy with the bus engine was actually fast. And soon, other racers started hunting for 702 engines. They'd scour bus depots, commercial truck junkyards, and industrial equipment auctions. The engines were still relatively cheap because nobody in the commercial world wanted them anymore. Diesels were taking over the heavy truck market. But for drag racers who understood what Hoover had discovered, they were gold. The beauty of the 702 for drag racing went beyond just its torque. Because it was designed for commercial use, GM had overbuilt everything. The bottom end was massive. The main bearing journals were bigger than a 454 big block. The connecting rods were beefier than anything in the passenger car world. The block was so thick that you could bore it out significantly without worry. Some racers took them out to 750 cubic inches or more. More racers began experimenting with the 702. They discovered you could actually make significant power improvements with relatively simple modifications. The stock cam was incredibly mild, designed for economy and longevity. Swap in a slightly more aggressive grind. Nothing radical, just something with a bit more lift and duration, and power would jump dramatically. The stock Rochester 4-barrel was sized for economy. Replace it with a larger Holly and the engine would wake up. Add headers instead of the restrictive stock manifolds and you'd gain even more. By 1963, modified 702s were making over 400 horsepower and 700 pound-feet of torque. Still at under 3,000 RPM. They were basically unbeatable in the lower drag racing classes. The National Hot Rod Association didn't know what to do with them. They were classified as aus experimental engines because they weren't available in passenger cars, but they were actually production engines. The NHRA eventually created special rules just for the 702, trying to level the playing field. And one of the most successful 702 racers was Jack Lufkin from California. Lufkin took the concept even further. He figured if one 702 was good, 2 would be better. He built a dragster with twin 702 engines. That's right, 2 V12s, 1,404 cubic inches total, 24 cylinders. The car was absurd. It weighed nearly 3,000 pounds, which was heavy for a dragster. But with over 1,200 pound-feet of torque available from idle, weight almost didn't matter. Nen Lufkin's twin-engine dragster ran 8.9 seconds at 156 miles per hour in 1964. To put that in perspective, top-fuel dragsters running nitromethane were only about a second quicker. And Lufkin was doing it on gasoline, with bus engines, shifting at 2,400 RPM. It was like showing up to a Formula One race with a bulldozer and keeping up with the field. The technical reasons why the 702 worked so well in drag racing are fascinating. First, the torque curve was essentially flat from 800 RPM to 2,000 RPM. This meant the engine was always in its power band. No waiting for the engine to come up on the cam like with high RPM engines. Second, the low operating RPM meant less stress on everything: valve train, pistons, rods, crank. While other racers were breaking parts trying to spin to 7,000 RPM, 702 racers were cruising at 2,400 and third, and this is the really clever part. The low RPM operation meant you could run massive tires. High RPM engines need steep gears to multiply torque, which means the tires are spinning faster, which means they're more likely to break loose. But with 700 pound-feet available from idle, you could run tall gears and big tires. The tires would hook up and stay hooked. The 702 also had some unique design features that helped in racing. The 60-degree V angle meant the engine was relatively narrow for a V12. The external dimensions were actually similar to a big block V8. The valve train was gear-driven, not chain-driven, which meant precise valve timing that never changed. The bottom end was cross-bolted with 4-bolt mains, something that wouldn't become common on performance V8s until years later. But perhaps the biggest advantage was psychological. Other racers simply didn't take the bus engine seriously until it was too late. They'd see this big, low-revving engine and assume it was slow. They'd hear that turbine-smooth idle and think it was mild. Then the green light would drop and they'd be watching taillights before they knew what happened. And then the 702's success in drag racing led to some interesting developments. Aftermarket companies started making performance parts. Crane cams developed special grinds just for the 702. Offenhauser made aluminum heads. Headers became available from multiple manufacturers. There was even a guy in Ohio who would convert 702s to accept dual 4-barrel carburetors, or even Hilborn fuel injection. And some of the modifications were extreme. The stock 702 used a single distributor driven off the camshaft, but racers figured out you could adapt dual points or even dual distributors for more precise timing control. The stock oil pan held 12 quarts, but racers made custom pans that held up to 20 quarts to ensure oil supply during hard launches. Custom pistons pushed compression ratios up to 10.1 or more, though this required aviation gasoline to prevent detonation. By 1965, the 702 had become enough of a force in drag racing that other manufacturers took notice. Chrysler engineers studied captured 702s to understand how they made so much low-end torque. Ford reportedly considered developing their own V12 for trucks, partly inspired by the 702's success. But GM ironically seemed uninterested in the racing applications of their bus engine. They discontinued the 702 in 1965, moving to diesels for heavy commercial applications. Then, the end of production didn't kill 702 drag racing, though. If anything, it intensified it. Now there was a finite supply of engines, which made finding and building one more challenging. Prices for used 702s jumped from $200 to over $1,000 by 1966. Complete running engines became hard to find. Racers started buying entire buses just to get the engine. One of the most innovative 702 builders was Frank McGurk from Detroit. McGurk was a former GM engineer who had actually worked on the 702 development program. After retiring, he set up a shop specializing in 702 performance builds. McGurk knew secrets about the engine that nobody else did. He knew, for example, that GM had experimented with different cam profiles during development and that one particular grind, never released to production, made significantly more power. Orshan McGurk also discovered that the 702 block could safely handle much more than its stock output. He built engines that made over 500 horsepower and 800 pound-feet of torque while still maintaining the low RPM character. His engines were so successful that he had a 2-year waiting list by 1967. Racers would ship him engines from across the country for his magic touch. The 702's influence extended beyond just drag racing. Its success proved that there was more than one way to go fast. It challenged the conventional wisdom that RPM was everything. It showed that torque, properly applied, could be just as effective as horsepower. This lesson wouldn't be lost on future engine designers. The modern diesel performance movement, where massive torque trumps high RPM, can trace some of its roots back to what racers learned from the 702. There's also the story of the 702 that almost went to Le Mans. In 1966, a privateer team from California had the crazy idea of entering a 702-powered car in the 24 hours of Le Mans. Their logic was that the engine's commercial-grade durability would give them an advantage in the endurance race. They built a custom sports car chassis and fitted it with a mildly modified 702. The car was actually quite quick in testing, able to hit 180 miles per hour on the Mulsanne Straight Tianwan-Anshan, but the Le Mans organizers rejected their entry. The official reason was that the 702 was a truck engine, not a passenger car engine, and therefore didn't meet the homologation requirements. The real reason, according to team members, was that the French didn't want to see a bus engine competing against Ferraris and Porsches. The car never raced, but it proved that the 702's potential extended far beyond the dragstrip. And back in America, the 702 continued to dominate certain drag racing classes through the late 1960s. But as purpose-built race engines became more sophisticated and rules changes limited the advantages of displacement, the 702 gradually faded from competition. By 1970, they were rare at major events, though some still competed successfully at local strips. The problem wasn't that the 702 had gotten slower. It was that everyone else had gotten faster. The development of aluminum heads, better flowing intake manifolds, and more radical camshafts meant that conventional V8s could now make comparable power while weighing hundreds of pounds less. The introduction of nitrous oxide systems and improved superchargers gave V8s the instant torque that had been the 702's advantage. And frankly, it was getting hard to find good 702 cores to build, but the legend of the bus engine lived on. Even today, there's a small but dedicated community of 702 enthusiasts who collect, restore, and race these engines. A good 702 core can sell for $10,000 or more. A complete running engine might fetch $25,000. That's a long way from the $200 that Tom Hoover paid for his first one. There are probably fewer than 100 running 702s left in the world today. Some are in museums, testament to GM's engineering ambitions and drag racing innovation. Some are still in vintage drag cars, coming out for nostalgia events, where they still surprise newcomers with their unique sound and brutal acceleration. A few are even still in commercial vehicles, mostly fire trucks, that were carefully preserved by collectors. Modern technology has allowed some interesting developments with surviving 702s. Electronic fuel injection systems designed for marine V12s can be adapted to the 702, improving drivability and power. Modern synthetic oils allow safer operation than was possible in the 1960s. CNC machining means custom parts can be made more easily than ever before. One builder in Texas recently completed a 702 with custom billet aluminum heads that makes over 600 horsepower while still maintaining the low RPM character. There's even been talk of someone attempting to 3D scan a 702 block and creating reproduction castings. The cost would be astronomical, probably $50,000 per block, but there are apparently enough interested parties that it might happen. It would be the ultimate tribute to an engine that was never supposed to be anything special. The story of the 702 teaches us something important about engineering and innovation. Sometimes the best solution isn't the obvious one. GM's engineers weren't trying to build a drag racing engine. They were trying to solve a practical problem, how to move buses efficiently through city traffic. But in solving that problem, they created something that challenged every assumption about performance. The 702 proved that torque, not horsepower, wins races off the line. It proved that durability could be a performance advantage. It proved that sometimes the answer isn't to spin faster, but to work smarter. These lessons influenced everything from NASCAR engine development to modern turbo diesel performance. When you see a modern power-stroke diesel making 1,000 pound-feet of torque at 1,600 RPM, you're seeing the spiritual successor to the 702 points engine. But beyond the technical lessons, the 702 story is about vision and creativity. It's about racers like Tom Hoover who saw potential where others saw a joke. It's about looking past conventional wisdom and asking, what if? It's about taking something designed for one purpose and reimagining it completely. That's the heart of hot rodding, really. Taking what you can find and making it faster than anyone thought possible. Nick and the GMC 702 Twin 6 remains one of the most unlikely success stories in drag racing history. A bus engine that humiliated purpose-built race motors, a low-revving truck power plant that out-accelerated high-winding performance engines, a commercial workhorse that became a quarter-mile warrior. It shouldn't have worked, but it did. And in doing so, it changed how people thought about going fast. And today, when you see a Tesla Model S Plaid launching with instant electric torque or a modern turbo engine making peak torque at 1,500 RPM, you're witnessing concepts that the 702 pioneered 60 years ago. The idea that massive low-end torque could trump high RPM horsepower. The notion that the first few feet of a drag race matter more than the last few. The understanding that sometimes the most unlikely solution is the best one. The next time you're stuck behind a city bus, listening to its diesel engine grunt away from a stoplight, remember that once upon a time, buses gave drag racers their greatest secret weapon. An engine that nobody wanted became one that everybody feared. A power plant designed for grandmothers going to the grocery store became the choice of racers going for glory. That's the beauty of engineering. Sometimes the most brilliant solutions come from the most unexpected places. The GMC 702 Twin 6 will forever stand as proof that in the world of performance, conventional wisdom is made to be broken, one bus engine at a time. What's the most unusual engine swap you've ever seen dominate at the dragstrip? Let me know in the comments below. And if you enjoyed this deep dive into one of racing's most unlikely heroes, make sure to subscribe for more stories of engineering marvels that changed the game. Until next time, keep those engines running, no matter how many cylinders they have.